Okay, so we haven't finished what we started last lecture. Okay. And last lecture we described disorder, and we have shown that there is a function defined by Claude Shannon, which is the disorder that eventually we call this disorder the entropy of the system, and it is S equals minus K Boltzmann, sum over I, Fi, log of Fi, where Fi, the probabilities of the different states that we have inside for our system. Very nice. Now, the next step was that usually how we define ensembles. Now, ensembles we define, well, we know how we define the microcanonical ensemble. For the microcanonical ensemble, we simply said, look, all the different Fi's are exactly the same. We have a uniform distribution. This was a microcanonical ensemble. The canonical ensemble, we used a more physical description. Right? We basically said, we have here a conditional probability. We have a big system, which we call the heat bath, and we have our system. Okay? So this is system, this is heat bath. And then we use that there is some quantity that we call temperature, and the temperature is equal in the heat bath and inside our system. And using this and this conditional uniform distribution, we found all the different Fi's. So this was the method that we used so far in order to describe and define different ensembles. Now, the thing that we started doing last week is to say, but we can use it in a way better form. If you look on this definition of entropy and accept it, that this is the microscopical definition of entropy, we know that entropy has to be maximal. Okay? In equilibrium, this is one of the consequences of the second law of thermodynamics, that the entropy is maximal. Okay? So if the entropy is maximal, let's use this principle in order to derive all the different Fi's, right? And using some specific constraint. So, first thing that we have done, we said that let's look on this delta S as a function of the different variations of different probabilities, Fi's. Okay? Now, all the Fi's have to satisfy something. So the constraint that is always has to be satisfied. So this has to be equal to 0. We're not looking for minima, using for maxima, but in the similar fashion as in analytical mechanics, we're looking for extremum, and we assume that this extremum is going to be maximum. Now, the constraint that we had is simply that a sum over Fi equals to 1. This is it. Everything else in our system has to be constant, not constant. We're not assuming anything. So if we have only this constraint, so we know that the entropy has to be maximal, and the only constraint that we have that the sum over Fi have to be 1, okay, we can use this as our starting point. So let us see what happens if we only assume those conditions. So maximal delta S and a specific constraint over Fi, which is simply the normalization. Okay? So what happens for this specific regime? So delta S equals to delta minus K Boltzmann, sum over Fi, log of Fi. Remember, Fi are different probabilities, and we vary them somehow. Right? So we can vary F1 by a specific amount and F2 by a completely different amount. So eventually, the different variations over different Fi's are going to be independent. Okay? So, and this is important to remember. All the different Fi's are independent variables, and we can vary them as we like. Right? They do not depend on each other. The only dependence that we have is this guy, at least for this scenario. Okay, so what happens over here? So it is simply minus K Boltzmann. This is a sum, and we assume that the variation of the sum is the sum of variations. So it's a sum over I. delta over fi log of fi. Let's continue this a little bit more. So this is minus K-Boltzmann, sum over fi. So a variation, it's like taking a derivative and then multiplying it by variation of the inner variable. So we have a multiplication over here. So it is simply log over fi multiplied by delta fi plus fi multiplied by the derivative of this guy, so 1 over fi, multiplied by delta fi. Okay. So in total, we're getting that this is minus K Boltzmann, delta S, minus K Boltzmann, a sum over I, and here we have log of fi plus 1 multiplied by delta phi. Okay. So this is the variation of the entropy itself.
Or microtheoretical stuff.
Wait a second. Okay. Wait a second. Right. So eventually it's going to be for microtheoretical. But, so this is the variation of delta S. And we are looking for minima or maxima, general and extremum of S, but we have to use this constraint. Okay. Now, remember how we already showed that, how we use or how we implement constraint in finding an extrema. We use Lagrange multipliers, right? So basically we can say, let's find the variation of this of this quantity. Okay. So the variation of this quantity, delta of a sum over I fi, equals simply a variation of a sum is a sum of a variation. So if it's a sum of delta fi. So in order to find the extremum of S, while this constraint is satisfied, okay, so what I do in general is basically I say the following thing. I assume that I'm looking for a variation, delta, of S plus some lambda, let's call it lambda 1, of a sum of I f. Right? And the variation of this quantity has to be 0. Okay? Now, it's a variation of a sum, so a variation of a sum is a sum over variations. So I know it equals to minus K Boltzmann, sum over I, log of fi plus 1 delta fi. And here I can say this is plus lambda 1, a sum over I, delta fi. And all of this equals 0. Okay. So we see we have exactly the same sum. This is the same index. And here we have delta fi, here we have delta fi. So we can identify those two sums as one single sum. So we have over here a summation over I, log of fi plus 1. And here I have plus lambda 1 tilde, all of this, or minus lambda 1 tilde, all of this multiplied by delta fi. And this equals 0. Now, yes?
You need to multiply with the K Boltzmann.
Exactly. But this is constant, so I don't know exactly what constant is. Okay, so I'm basically saying that lambda 1 tilde equals to minus lambda 1 multiplied by K Boltzmann. Right? It's a specific constant in Legendre multipliers, Lagrange multipliers, I'm sorry, and eventually we will reach some formula for it. Okay. All right. So we look on this formula and we say this has to be 0 no matter what the different variations are. So all the delta fi's are completely independent from each other. Why? Because we implemented beforehand they were somehow correlated or dependent because this condition has to be satisfied. Now, the moment that we use Lagrange multipliers, two Frenchmen, Lagrange multipliers, we don't think of it as of different fi's as dependent variables. They became independent. This is the magic of Lagrange multipliers trick. right? So when we look on the different variations of the FIs, we say they are completely independent. So we have a sum. Inside of the sum, we have something that depends on Fi multiplied by something that depends on the Fi, and all the different Fis are independent. Okay. Now, this has to be satisfied independently of what exactly representation I've taken for Fis. No matter how I use Fi, no matter what I substitute for Fi, this has to be satisfied, always. What it means that all the different summands has to be equal 0. Okay? So whatever stands inside those parentheses for each I has to be equal 0. Okay? So for each I, log of Fi plus 1 minus lambda 1 tilde equals 0. Okay? Now we can solve this equation. We obtain that Fi equals to e to the power minus 1 plus lambda 1 tilde for all Fi. Okay, so this is great. We obtained the distribution of all the different Fis are what? Are exactly the same. Okay, so all the different states that we have inside our system have the same distribution. This is exactly the microcanonical ensemble. Remember? Now, in microcanonical ensemble, I know what the different Fis are. Okay. Why I know? Because I know that this is, if all the different states are exactly the same, it has the probability to be in any specific state, it has to be equal to 1 over the number of different states that I have inside my system. Okay? How we see this? We know that sum over I over Fi equals 1. Okay. This leads to a sum over I e to the power minus 1 plus lambda 1 tilde, okay, equals 1. Okay. Now we obtain from that e to the power minus 1 plus lambda 1 tilde multiplied by n. Okay, so this is the number of states that we have inside the system. Number of where? Here? No, this is lambda 1 tilde. Okay, so here I had a plus, and here I just define it by some multiplied by a minus. It's a constant. Okay?
If we're already there, it's supposed to be divided by k plus, not multiplied by k plus.
Yes, you are right. You're right. You're absolutely right. Number of states in the system. Okay. Equals 1. Okay, so what we obtained that e to the power minus 1 plus lambda 1 tilde equals 1 over n. Okay, this means that minus 1 plus lambda 1 tilde equals minus log of n, and lambda 1 tilde equals to 1 minus 1 over n. Okay, and then we take this, we submit it to this guy over here. So Fi equals to e to the power minus 1 plus 1 minus log of n in the parentheses, and we obtain that Fi equals 1 over n. So by using this idea that we have the entropy, and the entropy has to be maximal with respect to Fis, and the only thing that we need to take into account are the different constraints that we have inside our system. And if the only constraint is, well, the summation over Fi has to be equals to 1, we're getting to the solution of microcanonical ensemble. Right? This is the result of microcanonical ensemble. All the different states are exactly the same. This is microcanonical ensemble. Very nice. Can we do it for canonical ensemble too? if we can, and it's actually going to be exactly the same answer as we get from a physical interpretation of a heat bathroom, etc., then we have a tool to construct ensembles, right? So let's do it. We have done it for very simple constraint, okay? And we obtain the microcanonical ensemble, and we know what happens in microcanonical ensemble. Let's do it now for a different constraint. Okay. We are performing exactly the same trick. We're saying we have the disorder, okay? We have the disorder. This is our disorder, okay? We want to know what are the different FIs are for the disorder. We know that the entropy has to be maximal, so this has to be satisfied. We know that the normalization always has to be satisfied, okay? But let's introduce an additional constraint. The additional constraint is going to be that we have different energies in our system. Okay? We can have different states and we can have different energies associated with those states. Okay? So let's say that a summation of Fi multiplied by EI. Okay, so we introduced energies associated with different states. Okay. So we know that the average energy is going to be constant, and this constant we are going to call it U. It's a parameter, right? So we have a parameter. Let's not say constant, let's say the parameter. We have a parameter in our system, and we know that the value of the average energy is U. Okay? So what we do have now, we have this constraint. Okay? We have this, this is the maximal that we're looking for. This is the additional constraint. And another constraint that we include in our systems is that we have an average energy. So look, I'm not telling you anything about entropies and etc., etc. This is a pure statistical approach. Right? We're looking at the different states of the system. We say they have probabilities, and the probabilities has to be constrained somehow, okay, by parameters that we include inside our system. What are the different constraints? Normalization and average energy. Average energies already brings us somehow to something physical because we have energies. Okay? For the microcanonical state, there is nothing. Pure statistics. And we know from the definition on Shannon that the maximal entropy for simplest case is always going to be where the distribution is uniform. I can be anywhere. This is the maximal entropy, maximal disorder. I can switch everything and still the state is going to be exactly the same. Here it's something different. We implement physics. Okay? So this is already not pure statistics. We implement physics. And let's see how it works for us. Okay? So delta S stays exactly the same. Okay? So this is the first, this guy. Okay? This we have. What else? Let's go forward.
Stas, איפה אנחנו שאנחנו פה בצבר מיקרוקנוני?
We arrive. No. It's the other way around. We use constraints to define ensembles. We use only this constraint, and we arrive to microcanonical ensemble. We use two constraints, and let's see where it's going to get us. Okay? So it's the other way around. I'm not saying I'm in microcanonical ensemble, and look what I'm getting. No, I having specific constraints, and look, let's see what ensemble I will get. Okay? So it is the way to define ensembles. It's not the way to use ensembles to define something. Okay, so delta S, this is delta S. Delta F stays exactly the same. Let's write it down. Delta F, delta of a sum over I, Fi, is exactly sum over I, delta Fi. This stays exactly the same. Okay? And we have this constraint. Okay, so delta U, okay, equals to delta over sum over I, Fi, Ei, which is simply, because it's a variation of a sum, it's a sum over variations. So it's sum of Ei delta F1. All right. Now we again use this trick of Lagrange multipliers. Right? We need to find extremum of this function. We have two constraints, so we have two multipliers right now. Right? So let's see. So we want to say the following thing: delta S plus lambda 1 delta over sum over I Fi plus lambda 2 over delta U, all of this equals 0. Right. So beforehand, all the different Fi's were connected to each other due to the constraints. We include this Lagrange multipliers, and we are free now. Okay. Wonderful trick. So let's write down this equation using this formula, and this formula. Okay. So in total, what we're getting that minus k Boltzmann, a sum over I, log of Fi plus 1 plus lambda 1 plus lambda 1 multiplied by, write it down, plus sum over I, lambda 1 delta Fi plus sum over I, lambda 2 Ei delta Fi, all of this equals 0. Okay? So we have three sums, and of course those three sums are exactly one sum.
You're missing delta I maybe? The delta F?
Delta Fi, yes. Thank you. Delta Fi. Because they are constant. Okay, so how I define? I need to define a system, and for this system I define the energies. The energies are not going to be modified. I have a specific system in mind, and I'm looking on the so what can be modified are the probabilities. The system is constant. Right? I have this specific system with this specific sets of energies. I'm not modifying energies. Right? This is important. I'm looking for the different probabilities for a specific representation, for a specific system. So the energies are not modified here. Important question. Great. So I have a total sum now. Okay. Let's see what it looks like. So minus k Boltzmann. So sum over I. And what I have inside. Log of Fi plus 1. And here I will have minus lambda 1 tilde minus lambda 2 tilde Ei delta Fi, and all of this equals to 0. Okay. Yeah, looks reasonable enough? Or you want, let's do it plus and plus. Okay. So what is lambda 1? Lambda 1 tilde equals to minus lambda 1 divided by k Boltzmann, and lambda 2 tilde equals minus lambda 2 divided by k Boltzmann. Okay, now again the same trick. We use the Lagrange multipliers, and Fi's are independent. This sum has to be equal to 0 no matter what the different Fi's are. That means that the summand always has to be 0. This means that whatever is inside here for any I has to be 0. Okay? So for all I, log of Fi plus 1 plus lambda 1 tilde plus lambda 2 tilde Ei equals to 0. Okay? This is an easy equation that we can solve. What's the solution of this equation? Fi equals to e to the power minus 1 minus lambda 1 tilde minus lambda 2 tilde Ei. So it's already reminds us of the solution for the canonical ensemble, right? This is constant, and we have e to the power minus something multiplied by ei. This can be related to the temperature, maybe, all right? But this is a nice representation, okay? Okay, how we deal with this? How we obtain the different values of lambda 1 tilde and lambda 2 tilde. Remember, beforehand I've used the normalization in order to define what is lambda 1. Right? So I needed some sort of a physical or additional information. What kind of information I'm going to use now? Okay, so this is not enough. This was for microcanonical ensemble. I cannot simply use this. Right? So this goes away. I need an additional condition. I need some physical information. Because I used it only for when all the different FIs were exactly the same. If you look beforehand what I have done, I can use this interpretation, only when all the different FIs are exactly the same. They are different now. So I need a different physical or a different additional information. Here comes some sort of physics, right? Because I know from thermodynamics, yes?
Why can't you just put the FI that we found in the zip?
Okay, great. So you want to say the following thing. You want to say that sum over I, Fi, EI equals to U. Okay. Now let's put it here. So we have a sum over I, e to the power minus 1 minus lambda 1 tilde minus lambda 2 tilde e I multiplied by ei equals U. Right? Okay, so this is a great idea. This is a great idea. Okay, this is a great idea because we can use somehow this equation in order to define this, and an additional constraint. Additional constraint is going to be what? A sum over I, e to the power minus 1 minus lambda 1 tilde minus lambda 2 tilde ei equals to 1. So basically, this is what we need to perform, okay, in order to obtain what are the lambda 1 tilde and what is lambda 2 tilde. But there are some easier ways. So you're right, absolutely right. We need somehow to find the different lambda 1 and lambda 2 by using those constraints. Okay? But we can use something a little bit, here is a trick, that we can use something else in order to define our lambda 1 and lambda 2. It's similar but a little bit different. A little bit different. So from physics, what do we know? We know that dou S, so du, equals 1 over t. I want to introduce physical quantities. I can find different EIs or lambda 2 based on u, but I want to introduce physical quantities. And one of the major physical quantities is temperature. Okay, so S, I already know what it is, right? I have a general definition. U, I can maybe obtain it from the S, okay? And then I can find the temperature and define everything by the terms of temperature. I want to use physics. So what is S? Minus K Boltzmann, sum over I, Fi, log over Fi. Okay? So let's now take this Fi, put it inside here, and see what happens. Okay? Because then maybe we can obtain the S in terms of U. So what happens right now? So we have minus K Boltzmann, sum over I, Fi, and I leave it for a second. For a second, this Fi I'm not going to modify, but the log of Fi, I'm going to use this quantity. So this is a log, and you will see in a second why. E to the power minus 1, minus lambda 1 tilde, minus lambda 2 tilde, ei. Why I'm using that? because it's minus k Boltzmann, sum over I, fi, a log of e to the some power. It always what? It's just whatever I have here. So I have minus 1, minus lambda 1, tilde, minus lambda 2, tilde, ei. Okay? So this is a sum, but this is basically two sums. So this is minus k Boltzmann, minus or 1 plus lambda 1 tilde, sum over I, fi, plus lambda 2 tilde, k Boltzmann, sum over I, fi, ei. This is already very nice. Why it's very nice? What is this quantity over here? It's u. This is 1. Okay, so now I'm using the constraints. You see? Now I'm using the constraints. So this is k Boltzmann, so we have S equals to k Boltzmann 1 plus lambda 1 tilde plus lambda 2 tilde k Boltzmann, okay, multiplied by u. So ds to du equals 1 over temperature. And it equals to, according to this equation, to what? To lambda 2 tilde k Boltzmann. So lambda 2 tilde is 1 over k Boltzmann to the power of t. Okay? So we can go backwards and see what is the fi now. What is this fi? So fi equals to, we have e to the power minus 1 minus lambda 1 tilde multiplied, I want to use it, it's like you say, but multiplied by e to the power minus beta ei. Okay? Where beta is 1 over k Boltzmann t. Okay, so this is a constant, independent of the different energies. So this is a normalization constant. And this is what? This is the probability that we obtain from the canonical ensemble. Right? So this is a canonical ensemble. This is a normalization. This normalization is going to be something that depends on lambda 1. But we can actually say, well, we can do even a little bit better. Why we can do a little bit better? Because look on this equation over here. This one. Let's write it down again. So we have S equals to k Boltzmann 1 plus lambda 1 tilde plus lambda 2 tilde k Boltzmann u. Lambda 2, we already know what it is. So lambda 2 tilde is 1 over k Boltzmann t. The only thing that we don't know still over here is this quantity minus 1 minus lambda 1 tilde, which is basically e to the power minus 1 plus lambda 1 tilde. So we have 1 plus lambda 1 tilde. This is our unknown. We look on this equation. We have it exactly 1 plus lambda 1 tilde. Okay? This is exactly 1 plus lambda 1 tilde. So we know now that 1 plus lambda 1 tilde equals to S divided by k Boltzmann. Okay? Plus minus u divided by what? U divided by t. Yes? Great. Or we can write it down like this. K Boltzmann, 1 plus lambda 1 cubed. S minus u divided by, so what is this? S minus u, t, and etc.
F divided by g.
Okay, so we remember F is u minus ds. Okay, F is u minus ds. So we can, from here, we know that S minus u divided by t is simply minus F divided by t. Okay. So what we obtain that K Boltzmann multiplied by 1 plus lambda 1 tilde equals to minus F divided by t, or 1 plus lambda 1 tilde equals minus F multiplied by beta. Okay, so now we have everything at hand. In terms of physical quantities. Right, so Fi equals to e to the power minus d ei. Here we have e to the power f divided by beta. F beta, I'm sorry. Right? F beta. Okay. And this is exactly what we have in canonical ensembles. Why so? Why so? So remember, F equals to minus 1 over beta log of z. Z is a sum over I e to the power minus beta ei. Okay, so let's do it. So we have sum over I, Fi, which equals 1, equals to a sum over I e to the power f beta multiplied by e to the power minus beta ei equals to e to the power f beta, right? And here we have multiplied by z. So it's satisfied. You see, the f that we obtained satisfied this function over here. So we obtain exactly the representation of a canonical ensemble. Right? So what we have done, we haven't assumed anything about constant temperature. We haven't had a heat bath. We had nothing. Right? We have a microscopical definition of entropy, a principle that we have to be in a maximal entropy. Maximal with respect to what? Maximal with respect to different probabilities. And we have one constraint. So normalization is always there. Okay? We have only one constraint. We simply said there are different energies. Those energies are constant. Okay? And we have a parameter in our system. The parameter is that sum of I, Fi, Ei equals to the average energy. Okay, so what we managed to, how we basically obtain this canonical representation. If beforehand we thought about it, oh, we have a heat bath and we have a constant temperature, now we can think of it, no, we have a distribution of probabilities and we have a parameter. And this parameter is the energy. The energy of the system now can be anything. And we only keeping constant the average energy. This is our parameter. Okay? Beforehand, for microcanonical, we haven't spoke about anything. Now we can say canonical representation always obtained when everything is kept constant except the energy. The energy can fluctuate, it can be whatever I want, as long as I define what is the average energy, which is U. Okay? Yes? Sorry? So this is exactly going to be 1. Oh. Yes, this is going to be 1 over z, and it's going to be equals 1. We have a minus over here. Okay? So this is why it works. This is why it works. Okay? So if you remember, for canonical representation, I had Fi equals 1 over z, right? E to the power minus beta pi. This is exactly what I've got over here. And my potential for canonical ensemble wasn't the energy. What is the potential of canonical ensemble? The free energy, this F that I have written over here. If you see how we developed in the first place the canonical ensemble, we said there is a natural potential for canonical ensemble. And this is the free energy. And this is the free energy that we are getting again by using completely different method. Okay. All right, so the outcome of all of this is that we have at hand a method to define ensembles. The only thing that we need to assume, what are the parameters, the average values that we are going to decide that we have inside the system. If we do not decide that we have average parameters and nothing is fluctuating, we're getting the microcanonical ensemble. For the microcanonical ensemble, the distribution is maximal. Then there is only basically one state, okay? And because the probabilities of being in different states are exactly the same. So effectively, nothing changes if I swap everything. This is a microcanonical representation. We go a little bit deeper, we say, no, we can also assume that the energies can fluctuate. The total energy, the energy of the system can be different. Right? But we use a specific, instead of saying the energy is constant, we're saying, well, the average energy is constant. We have a parameter. We can modify it afterwards. But if we calculate the distribution for a specific U, we're getting what? We're getting the canonical ensemble. And we have seen so far that the canonical ensemble is much more applicable. It's much more easier to use than the microcanonical ensemble. We can solve huge number of problems using the canonical ensemble. But sometimes it's not enough. Sometimes it becomes difficult to use the canonical ensemble. Sometimes the system not keeping specific parameters. So here we say the system can exchange energy with the outside world. What will happen if the system not only exchanges energy with the outside world, but also exchanges particles? Okay. So our question now, what kind of ensemble we can define? I write it down. What ensemble we need in order to deal with systems that exchange particles. Because sometimes it's difficult to treat systems where the number of particles is kept constant. Why? Because it was difficult, if you remember, to deal with systems where the energy was constant. We are running into combinatorial problems which are difficult, extremely difficult to solve. So the trick was, let's ease this constraint. Let's see that the energy can fluctuate. And then everything becomes much more easier. Much more stochastic, but much more easier. The same goes with number of particles. If we keep the number of particles, constant, okay, we are in trouble, because this is something that we have to satisfy all the way. No matter what the different states we are using, we must remember that the number of particles are constant. And sometimes it's very, very difficult. We will see. So the trick is again the same trick as we've done for canonical ensemble. We will say, let's forget about this constant. Let's say that on average, the number of particles is constant. This is the meaning of equilibrium. In equilibrium, I have a steady state. Now in steady state, it does not mean that everything is kept constant. Everything is kept constant on average. Okay? So the number of particles in this marker is not exactly constant. If I look on the layer, I will see that there are some particles of the air basically sticking to it, and some particles are released. There is a constant process. And the only thing that matters to me that there should not be a constant or flow of particles out of the marker, which is not balanced by particles that are adjusting to the marker, right? So I'm saying, on average, instead of getting constant number of particles, I'm going to say, I need an ensemble where the number of particles, the average number of particles, is constant. Okay. And this is my second ensemble that I'm going to use. Okay. And we already have a tool at hand. How do we find this ensemble? So what we know? We need the delta S. We have an entropy, minus K Boltzmann, sum over I, Fi, log of Fi. This is the entropy. We have an additional constraint, which is sum over I, Fi, equal 1. We have a sum over I, Ei, Fi, equals U. We have a sum over I, Ni, Fi. So this is normalization. Always holds, has to hold. This is average energy. We assume that the system can exchange energy with the outside world, but we say that on average, the system, or the energy is U. We need a steady state, we need an equilibrium. And in this equilibrium, the energy is something. Okay? It's not varies as a function of time. And this is average number of particles. Okay. So this is the additional constraint that we now include. And for this additional constraint, we need to develop the new ensemble. Okay? Now, we're already masters of developing new ensembles, right? We know how to develop microcanonical ensemble. We know how to develop canonical ensemble. But the way is always the same. Take this guy, use Legendre Lagrange multipliers for this and this and that. Right? Make everything, all the different variables independent, obtain an equation, solve it, and use some physical intuition in order to define the different constants that you use for your constraints. Okay? So let's see how it works over here. Okay, so the moment I will have it, I know, so what's the question is, what are the different FIs? Okay? The moment I will have them, I can solve a huge number of new problems, okay? Which are going to be more difficult than the problems that we solved beforehand. And specifically, this ensemble, that we're going to name as a grand canonical ensemble, grand canonical ensemble, is going to be very useful in dealing with quantum statistics and quantum situations. Because in quantum, I stopped caring about particles. I'm starting to care about states and how many particles can occupy a state, right? And we will see that this is the more important question. And in order to deal with how many particles can occupy a state, I need this ensemble and not the regular canonical ensemble. Because if I'm going to use a regular canonical ensemble, I'm going to have that all the different states are somehow speaking to each other. Because if the particle is in this state, it cannot be in any other state. I have constantly to think about the total number of particles it took. So if one particle is in the ground state, it cannot be in the other state. When I use this constraint and say, only on average, the number of particles is constant, I stop counting them. And the moment I stop counting them, everything becomes much more easier. This is why we need this grand canonical ensemble. You will see it when we will come to examples. All right, so let's start. Right? So we need that delta S plus lambda 1 delta a sum over I Fi plus lambda 2 delta a sum over I Ei Fi plus lambda 3 as sum over I, ni, fi, all of this, delta, 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 all of this equals to 0. This is the equation. Simplest case microcanonical ensemble. One constraint, little bit harder. Canonical ensemble, two constraints. More hard. It's even more harder. The grand canonical ensemble. Don't worry, we won't get to 4 constraints. All right. So what we have over here, we already seen all of this before. So delta S is minus k Boltzmann, sum over I, log of fi plus 1 delta fi. This guy is very simple. So this is plus sum over I lambda 1 delta fi plus this guy we also seen. This is sum over I lambda 2 ei delta fi. And this is also simple because what are the different ends? I know now I'm looking on the different states as beforehand. I know for this state there is a specific energy, right? This is what we obtain for canonical ensemble. Now I'm defining a state by a specific energy and a specific number of particles. Okay? Because the number of particles can fluctuate. Different states are defined by the number of particles and the energy, not only by the energy. Right? So this is something different. Comes from this guy. For each specific Fi, there is a specific Ni. Okay? And I'm not varying this Ni. This is important to remember. As I haven't varied, like you asked me to, the Ei. Okay? I have a system, I have a specific set of states, which are now defined by number of particles and energies. Okay? And I'm not varying this configuration. I'm only varying the probabilities. Okay? So we have plus sum over I, lambda 3, ni, delta fi. All of this equals to 0. Okay, so as previously, we can take the delta fi's out, and we have a single sum. We have minus k Boltzmann, sum over I, and here we have log of fi plus 1 plus lambda 1 tilde plus lambda 2 tilde ei plus lambda 3 tilde. What we have here, ni. Delta fi, and all of this equals to 0. Now let's write down what is lambda 1, lambda 2, and lambda 3. Lambda 1 tilde equals to minus lambda 1 divided by k Boltzmann. Lambda 2 tilde equals minus lambda 2 divided by k Boltzmann. Doesn't matter because eventually we have a sum, right? And lambda 3 equals to, right? Lambda 3 equals tilde minus lambda 3 divided by k Boltzmann. Great. So the solution of this equation, again, everything is independent, so the only thing that getting cancelled, so in order for this sum to be 0, all the summands have to be 0, so for all I, whatever stands between these square parentheses is 0. Right? So it's for all I, log of fi plus 1 plus lambda 1 plus lambda 2 ei plus lambda 3 ni equals to 0, and fi equals to e to the power minus 1 minus plus lambda 1 minus lambda 2 tilde 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 lambda 2 ei minus lambda 3 tilde 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 ni. Right? So it is similar to the canonical representation, but here we have something additional, which is this ni. Great. What do we do next? We use the constraints, right? as you told me to, but we again use this trick. Remember, we use this trick, and by using this trick of writing S in terms of U and N. Okay? We are going to write this S in terms of U and N, and then we are going to take specific derivatives of S or specific derivatives of U in order to define or find what are lambda 1, what is lambda 2, and lambda 3. Okay, so S equals to minus K Boltzmann, sum over I, Fi log over Fi. Again, the trick is keep this S phi's as they are and use this Fi in the logarithm of log of Fi. Okay? Okay, so S equals to minus K Boltzmann, sum over I, Fi, and here we are introducing this guy. So here we have minus 1 plus lambda 1 tilde, minus lambda 2 EI, minus lambda 3 tilde NI. Okay. These are simply three sums. So this is minus or plus K Boltzmann, 1 plus lambda 1 tilde, sum over IFI, plus lambda 2, K Boltzmann, sum over I, Fi, EI, plus lambda 3 tilde, K Boltzmann, sum over I, Fi, Ni. Okay? And we obtain that S equals to K Boltzmann 1 plus lambda 1 tilde plus lambda 2 tilde K Boltzmann. What is this sum? Fi multiplied by EI? U. Great. Plus lambda 3 tilde K Boltzmann. What is this sum? N. Okay? Those are the constraints. Okay. Now, we can look on this and we say ds to du equals to 1 over t. Okay. So look on this guy and what we are saying that 1 over t equals to minus. Why minus?
No, it's okay.
It's fine, right? Lambda 2 tilde K Boltzmann. Okay, so lambda 2 tilde equals 1 over t K Boltzmann, which is equals b. Okay. What else do we have? So t, remember, T is the field that is related to entropy. So there is a relation between S and U, and something that related to temperature always stands over here. This we know. Now there is also a relation between U and N. Yes. So du to dn equals mu. Great. We can use again this equation to take a derivative of u with respect to n, and we can obtain what are the lambda 3 K Boltzmann. Right? So we take the derivative of everything with respect, a partial derivative with respect to n. Let's go. Okay, so what we have over here, you want to write it down as, let's write it down as we already know. So we already know what this guy is, right? So S equals to K Boltzmann, 1 plus lambda 1 tilde, plus lambda 2 K Boltzmann equals to 1 over T, U plus lambda 3 tilde K Boltzmann. And, okay, so U equals to, what u equals to TS minus TK Boltzmann 1 plus lambda 1 tilde minus, right, minus lambda 3 tilde K Boltzmann T multiplied by N. du to dn equals to mu, and it equals to minus lambda 3 tilde K Boltzmann T. So lambda 3 tilde equals minus mu divided by K Boltzmann T equals to minus mu beta. Okay, so we have lambda 1 tilde, lambda 2 tilde, oh, no, lambda 1 we don't have, lambda 2 tilde, lambda 3 tilde, okay, and somewhere I erased what was the Fi. What was the Fi? Over here, okay, so we get this guy, I still need this one, right? But this is already easy. See this equation. K Boltzmann, this is the unknown. This we know, this we know, this we know, and now we already also know the lambda 3 tilde. So we have S equals to K Boltzmann 1 plus lambda 1 tilde plus 1 over T U, okay, minus, right, what we have here, minus, instead of lambda 3, what we write, mu divided by T, N. Okay. What? Why? So lambda 3 is mu. Okay, so what is beta? It's y 1 over K Boltzmann T, and K Boltzmann, right? So they kill each other. They cancel each other out. Okay, so from here, what we're getting that S divided by K Boltzmann, minus beta u, minus beta u, minus or plus beta mu n equals to 1 plus lambda 1. Now we're going to this equation. And we substitute everything that we have. Fi equals to e to the power minus 1 plus lambda 1, which is S divided by K Boltzmann, minus beta u plus beta mu n, okay, multiplied by e to the power. Lambda 2 is what? Lambda 2 tilde. Lambda 2 is beta. So we have minus beta EI minus, and lambda 3, what is lambda 3? Minus mu beta minus mu beta Ni. Okay, so this is what we get. All right, so if we have a grand canonical ensemble, for this grand canonical ensemble, we look for the maximal entropy under three constraints: normalization, average energy is U, average number of particles is N. So the system can exchange particles and it can exchange energy. We obtain the different probabilities are Fi, okay, which are e to the power minus, let's take here beta out, beta, and here we have inside U minus what we have, ds minus mu n. What is this?
Yes.
Psi. What is psi?
Potential for the grand canonical.
Potential of the grand canonical ensemble, which is a Legendre transformation of energy. Free energy was a Legendre transformation of U, U minus Ts. Now we have U minus Ts minus mu n, and it's a Legendre transformation of the energy. This is the new potential of our ensemble, right? We're getting it from the normalization constant here. Multiplied by e to the power minus beta ei minus mu ni. So if we call now psi, we call it u minus ts minus mu n, grand canonical potential. We are getting that Fi equals 1 over z e to the power minus e minus beta ei minus mu ni, whereas z equals a sum over I e to the power minus beta ei minus mu ni. Okay. And we are also having that log or psi equals 1 minus beta of log z. Those are the equations of the grand canonical potential. So we have math and physics tied together. What is the math? We have a specific constraints. Great. And we found a maximal of some crazy function defined by Claude Shannon 50 years or 60 years ago. Fantastic. But we also tied it up to physics, right? Because we are looking at it, we are saying there is a new potential now. It's not energy that's important. It's not the free energy that's important. It's the grand canonical potential that's important. Okay? We are not, when we're looking on the canonical potential, we are not looking on the entropy. We're forgetting about the entropy. We are transforming it to the temperature. This becomes our parameter. This becomes something that is constant. The same goes with the n. The energy was dependent on the number of particles. The moment that we are letting this number of particles do whatever it can, instead of looking on the number of particles, we have to look on the new parameter, which is mu, okay, which is the chemical potential. Okay? And we will see how it comes around. Okay? So we have no two coordinates which are intensive and not extensive. T and mu, new fields, we can say. So whatever we have done in canonical ensemble, now we are capable of doing in grand canonical ensemble. Everything is the same. The only thing that's we have to remember, number of particles is not constant. So each state is defined by a specific number of particles at this state. Okay? We'll see how it works. The partition function now is different. We have ni's over here. the potential that we are using in order to define all the different physical quantities is now not the free energy of Helmholtz, is this guy, which is a Legendre, and it's always a Legendre transformation. Remember, any potential that we can use is always a Legendre transformation of the psi over 2. So we're not going, so we now have two things at hand. One, the knowledge how to define ensembles. So if in an exam I ask you, let's define an example where the volume of the system, okay, is not constant. It's going to be fluctuate. You know how to do this. It was a question last year, I think. Okay. B, you know how to do with systems where the number of particles is fluctuating. We already have this representation. Okay. So now we're, in the last 15 minutes or so, we're going to see how we use this grand canonical representation in order to solve problems. So we reach the stage that we are dealing with quantum gases. Any questions about the grand canonical representation?
אמרנו שנכנס לנו פה בעצם הפיזיקה ושתייחסנו עכשיו לגורמים אחרים כגורמים, יכולנו להגיש את זה.
Exactly. So we use the constraints, how the physics got in. Look on the grand canonical potential. How we obtained this new, what does grand canonical potential means? That instead of using the U representation, okay, the energy, we're using a new coordinates. Okay, so if beforehand U was dependent on S and N, right? N now is a parameter that can change, right? It can be modified because. So instead of talking about N and S, we're talking about new potential that the new parameters are the temperature. Remember, we said there is some temperature inside the system. A new parameter, chemical potential, that is related to the number of particles that you have inside the system. The moment that everything can be modified, those are the new parameters of the system. And that's the physics. Right? The physics is, you say, I have new average quantities. I lose the constraint. I do not care about a constant number of particles. I do not care about a constant energy. I want to do something different. I can let my energy fluctuate. I can let my energy to go up or to go down. And the only thing that I care that on average, my energy won't change. The moment I say so, okay, I obtain new potentials, okay, and new probabilities. Okay. So we start with a very easy example, quantum gases. We will solve eventually 2 or 3 systems with quantum gases. But in quantum gases, we already know that we are talking about quantum particles. So that if beforehand we couldn't care less about the different particles, now we have to consider what happens if we have fermions in our system. What happens if we have bosons in our system? Right? Or what happens, nothing else can happen, right? Because we know in quantum mechanics only bosons and fermions. So how we deal with those specific systems where we have, for example, and this is the first case, is fermions. Now for fermions, there are very strong restrictions, right? What is this Pauli restriction? We know that 2 fermions or 2 electrons cannot occupy exactly the same state. Okay? Well, state is quantum mechanically defined by my system. So if I have a system, quantum mechanics, and I know that I have particles that are fermions inside, and I have a specific state inside my system, I know that it can be the occupation of the state can be either 1, where there is particle inside the state, or 0. This restriction is extremely, extremely, extremely strong. Why? Because it imposes a strong interactions between the particles. right? So it's basically saying the moment that the state is occupied, nobody can come and also join this specific system. So no matter where it sits, it's extremely strong interaction. Think about it as like a potential. Okay, so if I have a particle over here, and I have another particle that tried to approach it and occupy its position, or come nearby, there is like a delta function potential that the particle cannot cross. It's very, very strong interaction. Okay? Now this is why the grand canonical potential is going to be applicable. Okay? So even if our particles, fermions, are not interacting, in the sense that if you have a gas of fermions, they do interact. In quantum mechanics, they always interact because they cannot occupy the same state. And this restriction, this basically means that I restrict the degrees of freedom. And this means that I have strong interactions between the particles. So a gas of fermions, although they do not have an interaction, it's still an interacting system, or a system of interacting particles. We have to remember this. We have always to remember this. So our toy model, this easy example, is a system that there are only 3 energetic levels. So the state defined by the energies, and we have, this is our energy, epsilon 1, and we have epsilon 2, and we have epsilon 3. Now we are going and asking the following thing. How we define, and the number of particles can be, we use the grand canonical potential, whatever we want. Okay? There is only some restriction about the average number of particles, or if we want, we have a specific chemical potential. We have a specific mu inside the system. Okay? Basically, I can say the number of particles is whatever I want. And I ask you how to define a partition function of such a system. Okay? Because the moment I know the partition function, right, I know the different FIs. And that's it. Right? I can solve everything the moment I know the probabilities. Because the moment I know Z, I can use either this definition to find the probabilities, or either this definition to find the grand canonical potential, take the different derivatives, use all the tools that I learned from thermodynamics, and know absolutely everything that I want, or capable of. Right? So the quest is always to find the partition function. Okay. I have 3 different energies, and I ask myself, what is the partition function for this case when my particles are fermions? Okay. So basically, I need to count all the different specific distributions where Pi and UNI. Now remember, and this is the strong interaction. The moment I put a particle on a specific state, okay, I know that no other particles can occupy this. Okay, so this is a state of the system. The state of the system, I have one single particle sitting in epsilon 1. Okay, no other particles are occupied. So for this specific representation that I plotted here, the total energy of the system is what? Epsilon 1, and the number of particles is 1. Okay, so when I'm constructing this partition function, I know that there is a specific state, the energy is epsilon 1, and here I put 1. Okay? If I put here an additional particle, I cannot count this state. Why? No 2 particles can occupy the same state, the same energy, right? So this is impossible. But if I put another particle in this state, right? This is a state of the system. The energy of the state is what? Epsilon 1 plus epsilon 3. The number of particles is 2. Okay. So now I have to go over all the different combinations of where I can put all the different particles, okay? And what is the energy for each combination, right? And then I have to sum over all the different representations. Sounds like a nightmare, right? Especially if I increase the number of states. It's hard. Okay, so there must be some sort of a trick over here. There must be some sort of a trick. Okay. But let's start with what we know so far. So we need to write this Z, and we need to go over all the different possible states of the system. Okay, so when we are dealing with hard problem in statistical physics, remember there is only one way out. Always only one, well, two ways, and we will learn about the second, but the other way is not so correct sometimes. But there is definitely one way out, and this way out is to say, I want to represent everything in terms of single particle partition functions. Right? I know only one single trick, factorization. This is what worked for us in canonical ensemble, and this is also what's going to work for us in the grand canonical ensemble. Only factorization, nothing else. Okay? So when I'm looking for the Z function in order to sum it somehow, I need to use in my mind something about factorization. Now, there were two parts that led me to factorization in canonical ensemble. It's that I managed to separate the energies of the system into single energies that are independent from each other. Right? I had to play some tricks. Sometimes I had to add energies. Sometimes I had to subtract energies. Sometimes I had to represent the energies not of the particles, but some, like in the bimodal, by the energies of the waves, and etc. But it always the same line of thinking. Write the energy as a sum of energies that are independent from each other. That's it. Okay? So this is also what works over here. What is the energy, or even here, what is this EI minus mu EI? So the energy, the total energy of the system is what? Is N1 multiplied by epsilon 1 plus N2 multiplied by epsilon 2 plus N3 multiplied by epsilon 3. What are the N1? N1? Exactly. N1, it's either 0 or 1. We can say it's like an indicator function. And this is the number of particles that occupy level I, energy level I. Okay. This is the total energy. So if you write EJ, or J over here, and here we write EI. So EI is a specific state, is a specific energy, and you see that this specific energy is represented by a specific set of numbers, N1, N2, and N3. Okay? For each specific 3 numbers, it defines a specific energy. But the state is not only depends on the specific energy, also depends on a specific number of particles, right? So we have here Ni, right? Ni, we are going to say the specific state EI Ni, because EI depends on the number of occupation, or this occupation number, N1, N2, and N3. Ni is simply a sum, N1 plus N2 plus N3. Okay. So if we have a specific energy, for this specific energy, we also have a very specific, what? We have a very specific number of particles. So look now, we have this formula. Z, it's a sum over I. I is the different states, the different energies of the whole system where we have a specific number of particles. e to the power minus beta ei minus mu ni. We know what ei is, and we know what ni is. So we write it down in the following fashion. Sum over I, e minus beta. Instead of bi, what we write? n1 epsilon 1 plus n2 epsilon 2 plus n3 epsilon 3. Now, let's write down some indices that we know that this is n1 for state I. So this is a specific number of particles that sit on level 1 for the general state of the system that we term I. Okay. So this is Ni epsilon 1. Now what we have here, minus mu, and here we have N1 I plus N2 I plus N3 I. What happens next? We have sum over I e to the power minus beta, and we separate this into 3 different sums. Minus beta, and we have n1 I epsilon n1 I epsilon 1 minus mu multiplied by e to the power minus beta n2 I epsilon 2 minus mu multiplied by e to the power minus beta n3 and I epsilon 3 minus mu. I have done nothing wrong from going from here to here to here. But the moment I reach this expression, effectively I'm finished. Why? Because remember, each set depends on a specific values of n1, specific values of n2, and specific values of n3. But the n1 and n2 and n3, they are completely independent of each other. Right? I need just a set of n1 and n2 and n3, and that's all. But the n's itself, the total state depends on all the different representation of position of particles. But the n's, the different n's over here, they are independent. Okay? They are completely independent. N1 can be either 0 or 1, and it's completely don't care, okay, this state, completely don't care if this state is occupied or not. If I put a particle over here, I don't care if there are particles here or there are particles there. I simply don't care. Right? So the moment I write it, I written this expression, this is a factorization. This is a factorization in terms of n's. Because this is simply equals to sum over n1 from 0 to 1 e to the power minus beta n1 epsilon 1 minus mu multiplied by a sum of n2 from 0 to 1 e to the power minus beta n2 epsilon 2 minus mu multiplied by a sum over n3 from 0 to 1 e to the power minus beta n2 epsilon 3 minus mu. So I don't have independent particles, right? What do I have? Independent states. My states are independent. So instead of making a factorization of different representation of how the different particles are hitting here or there, I'm saying, look, the states are independent. If the states are independent, I'm going to look only on the states. I'm going to care only about the states, right? And for each state, I have each own partition function. I don't care about all the other states. I only care about this state. And this partition function is what? Is given by this number over here. And that's it. Right? Factorization is complete. we have now, what is this? Z1, it's a sum, n1 from 0 to 1, e to the power minus beta, n1, epsilon 1 minus mu, which is simply 1 plus e to the power minus beta, epsilon 1 minus mu. Z2 equals to 1 plus e to the power minus beta, epsilon 2 minus mu. Z3 equals 1 plus e to the minus beta, epsilon 3 minus mu. And Z equals to Z1 multiplied by Z2 multiplied by Z3. Great! I can write the partition function. But there is more. The moment I have made partition function as a factorization, I'm now considering each state as independent of each other. I only need the beta, I only need the mu. I now can treat, as in canonical ensemble, I can say, well, I have single particles. The moment I have a factorization, I have single particles, and I can look on the probabilities of being occupied, or of being particle at a specific place. I now can say, I can calculate the probability of this state to be occupied, or this level to be occupied. I can look on the probability of this level to be occupied, and etc., etc., etc. Because I can look on the partition functions of different levels, and I treat them as particles, or occupied and unoccupied. We will see how it gets along and what we are capable of doing by using this factorization, because now I don't care how many states I have. I could have 7 states, 80,000 states. It's going always to be factorizable. And the moment I have this factorization, I can do whatever I want. Whatever I want. I can calculate all the different probabilities. And we will continue with these calculations next week. Thanks. בבוקר. 9 וקצת.